Welcome back to the video series on integration and differential equations. Today we're going to look at separation of variables. This is exciting because it's our very first example of solving a DE. We are going to find an implicit solution. We'll talk about what that means as we go through the problem. So find an implicit solution to the following differential equation. dx equals 18xy to the fifth dy. First thing we're going to do here is we're going to divide both sides of the equation by x. So we'd have dx over x is equal to 18y to the fifth dy. At this point, we would say the variables are separated. What that means is that on the left side, we've only got x terms. We've got a dx and we've got an expression involving x. Whereas on the right side, we've got the differential involving y, we've got dy, and some expressions involving y. So if we say this differently, there are no y's on the left side and there are no x's on the right side. The variables are separated. So in moving from the first step to the second step here, what we want to think is that we want to get all the x's on the side where the dx is, and we want to get all the y's into the dy term. So by dividing through by x, we managed to separate our variables. Now that the variables are separated, we can go through and we can integrate term by term. So if the two sides of the equation are equal, then the integrals of those two sides are equal, meaning we're just throwing integral signs on here, and we're going to go through and integrate each of these two terms. All right, so on the left side, we're going to get ln x, and on the right side, we're going to get y to the sixth times 3 plus a constant. So let's make some comments about what we just did here. This is our first example of solving a DE, and we're going to see some really common patterns coming up here. So first comment, let's talk about what it means to have a solution. So this is the solution to our DE. And what that means, if we were able to isolate y, if we were able to solve for y here, and if we were able to solve for x, and then take the differentials of those two quantities to get dx and dy, then we could take those four quantities. We would take x, y, and their differentials. We could plug them in to our original DE back up here, and in plugging those four quantities in here, we would have quantities that satisfy that original differential equation. So that's what it means to have a solution. This guy here is the solution to our DE. Now in practice, we're not usually going to check our solutions. Often it would be quite difficult because of the form of the solution to check it. So what we can do, we can just check our intermediate work here, and then that would imply that our solution here is correct. So let's call that comment 1. We just talked about what it means to have a solution to the DE. Second comment, our solution here is an implicit function of x and y. What that means is that we've got an equation where x and y are tangled up, meaning we don't have an equation of the form y equals something. An equation that looks like this is explicit, and that is not what we have. We've got an equation where x and y are tangled up, so meaning an implicit function or an implicit solution. Okay, so the question told us it's fine to have an implicit solution, meaning we don't need to go through all the work of solving for y. It's fine to leave our answer like this. Third comment, notice when we were solving our differential equation in that very last step there, when we integrated the left side, we wrote ln x. Now if we think back to our ln form, right back towards the beginning of the video series, we said that formally when you integrate dx over x, you'd get ln absolute value of x, and then plus a constant here if we were being careful. So ln absolute value of x. What we're going to do when solving differential equations, we're going to omit the absolute value. So omit the absolute value in ln absolute value of x when solving DEs. This is something that's often done, especially in applied courses, just to simplify the solution process. Typically in applied contexts, our x values will be positive, so that's why it makes sense to use this convention here. Fourth and final comment, something that you may have noticed as we went through our solution process, we only use one constant when solving DEs. So if we look back at our very last step here where we moved from our integration to our solution, you could, for example, have written ln x plus c1 equals 3y to the 6th plus c2. So you could have put a constant on both sides there when we did those two integrations. But then what we would do to simplify is we would just subtract c1 from both sides. So on the left side, or sorry, on the right side, our constant would turn into c2 minus c1. And then we'd say, well, if c1 and c2 are both constants, what is c2 minus c1? It's just a constant. So we'd cross off that new constant. We'd say we don't need to call it c2 minus c1 anymore, and we'd just give it a new name like c3 or maybe c. And the thing is, we don't want to go through that reasoning process every time we solve a DE. So the convention that we come up with is that we just place one constant on the right side when we're solving these DEs, and it is rigorous to do that because that is equivalent to what you would get if you put constants on both sides. It's just overkill to put the constants on both sides and then have to go through the algebra each time. So we only use one constant when solving DEs. Before going on to another separation of variables problem, we're going to do a shortcut for ln form. So let's think back to ln form from the beginning of the video series. We said that the integral of du over u was equal to ln absolute value of u plus a constant. So for example, if we wanted to integrate 2x dx over, say, x squared plus 3, let's see if we can do this without doing a formal substitution, meaning let's see if we can do some of the substitution in our head. So we would let this expression in the denominator there, we'd let that be u, and then we'd ask ourselves, what's du? Du would be 2x dx. All right, so this looks perfect. On top, we've got du. On the bottom, we've got u. And we can go ahead and integrate this and say we're getting ln absolute value of the denominator plus a constant. So this shortcut works whenever the numerator here, whenever the numerator is the exact differential of the denominator. So let's see what's going to happen or what to do if the numerator is not the exact differential of the denominator. Suppose we wanted to integrate 3x dx over x squared plus 7. Okay, so first thing we do is we look at this and we'd say, okay, that's our u, and then what would du be? It would be 2x dx. So what I'm going to do in the numerator is I'm going to write down what we would love to have in the numerator. We would love to have 2x dx in the numerator. But in order to make this equality true, we can't just write 2x. So we have to think of that 3 here. Let's think of that 3 as 3/2 times 2. So I'm writing down what I want, and then I'm writing a correction factor so that it's still valid to write the equal sign there, so that we still got equality. So 2x dx is what we want, and then we're asking 3 is equal to something times 2. That would have to be 3/2 there. Okay, so if we fill in the denominator there, then we can go about our integration. We can say 3/2 is just a constant that's sitting in front here, and otherwise we've got perfectly the ln form. So we'd have ln absolute value x squared plus 7 plus a constant. So just to see whether we've really mastered that shortcut there, let's try the integral of 5x squared dx over x cubed plus 1. So to get this integrated, we would look at our denominator, it's x cubed plus 1. We'd ask, what would we love to have in the numerator? We'd love to have 3x squared dx. And then we could ask ourselves, do we have that? Well, no, we've got 5 on the left side here, and on the right side we've got 3. So what do we have to put here to make this equal? Well, 5/3 times 3 is the same thing as 5. So we're breaking that 5 up into 5/3 times 3. Okay, so that allows us to go through with our integration. 5/3 ln absolute value x cubed plus 1 plus a constant. So you're not required to do this shortcut. Of course, you're always free to do substitution, a careful substitution over on the side. If you feel more comfortable doing substitution, I encourage you to go with that. But there's always a benefit to being able to do your work efficiently as well as accurately. So if you are able to absorb this shortcut, I think you will find it helpful in some of your future work.